This is Dr. Masood Yusuf from the Division of Science and Technology, University of Education, Lahore. I'm going to be your instructor for the course Introduction to Material Sciences. Let's continue our discussion on mechanical behavior of materials. This video lecture will cover the following contents. Let's study an important theory regarding mechanical behavior of materials. It is Griffith's theory and Griffith's criterion. It is an energy-based theory that can be applied to find the length at which unstable cracks grow. What are unstable cracks? These are the cracks that can grow without any additional external input. We should also keep in mind fracture mechanics. Fracture mechanics are methods of analytical solid mechanics and are used to calculate the driving force on a crack, to characterize the material's resistance to fracture. Fracture mechanics was developed by English aeronautical engineer A. Griffith. A. Griffith explained the failure of brittle materials. Griffith compared the work required to break atomic bonds to the strain energy released as a crack grows. Griffith's work was built on two contradictory facts. What are those facts? The stress required to fracture bulk glass is about 100 megapascal, whereas the theoretically calculated stress needed for breaking atomic bonds in glass is about 10,000 megapascal. So there is a huge difference between fracturing a bulk glass, the stress required is 100 megapascal, and theoretically calculated stress required to break atomic bonds is 10,000 megapascal in a glass. This is a huge difference. Griffith proposed a theory and he tried to explain the difference between these two contradictory facts. Let us derive Griffith's energy release rate criterion. In order to derive, we will start by the definition of work. Work W is the mechanical form of energy and is simply given by W equal to F into dx. F is the force, whereas dx is the small patch element, small distance, and we can sum all the work done along different small patches with the help of integration. So this is the definition of work done. It is often convenient to calculate work or energy in terms of stress and strain. In order to represent work in terms of stress and strain, what we can do is that we can multiply and divide this equation with volume. The volume in division form can be written as area into length. This area can go under the force, and the force per unit area is called stress. Stress is usually represented by Greek letter sigma, whereas dx divided by L is the change in length divided by original length, which is the definition of strain. Strain is represented by Greek letter epsilon, as this strain is for small element dx, so we are using d epsilon. So we are also replacing W with U, as work done is energy, so we can replace W with U. So we have equation 1, which is U integration sigma into d epsilon V. Let's proceed further. Strain energy density can be defined as sigma into d epsilon, and let us represent strain energy density with U prime. So we have equation 1, and we can put the definition of strain energy. So equation 1 becomes U equal to U prime into V. For a linear elastic material in uniaxial tension, are a force which is acting only along one axis is called uniaxial tension. Hooke's law reduces to sigma equal to E into epsilon. This is very fundamental law which states that stress is proportional to strain, and when we replace proportionality with equality, we have replaced a constant, and that constant is modulus of elasticity. So this is Hooke's law, sigma into E into epsilon. So U prime can be rewritten as, if we replace sigma with E epsilon, we have this equation, and if we integrate with respect to epsilon, so we have this result: strain energy density is equal to half E epsilon square. We can also express this result in other forms, such as several different equivalent expressions can be written. U prime equal to half E epsilon square. This was the result. So if we put E into epsilon equal to sigma, then we have half sigma epsilon, and we can also write u prime as sigma square over 2e 2e. So equation 1 can be written as, if we put the value of u prime, so we have equation 1 as u equal to sigma square divided by 2e into v, which is equation 2. Let's move on to further steps. In order to break a bond, an amount of work equal to the bond energy must be performed on the system. So bond energy is equal to E subscript bond equal to 2 gamma S A B. Let us describe equation 3. So equation 3 gives the amount of work or energy that must be input into an object to overcome the atomic bond energy of the atoms forming a crack of length A. A is the length of the crack and B is the thickness of the part of the material. So in order to understand equation 3, let us have a look on this diagram, which is case of a crack growing in a solid. So you can see there is a crack growing in this solid material having length A. So we have arrangement of atoms which are represented by bluish balls. So each atom is have some bond with the neighbor atom. So crack of length A through several atomic bonds is appearing as shown in the figure, and B is the thickness which cannot be shown in this 2D slide. So just assume B is the thickness of the material. So this E bond, which is given by equation 3, is the amount of work or energy that must be provided in order to overcome the bond energy between atoms in order to form a crack of length A. Let us consider a bar under stress sigma. The bar is shown in the figure. You can see its strain energy will be given by equation 2. We have already calculated strain energy in equation 2, which is U equal to sigma square over 2E into V. Assume that a crack propagates all the way across the bar, causing it to break into two halves. So a crack is initiated in the bar and finally it is broken into two halves. Both halves will now be free from stress following the break. So after the bar is broken, so you cannot apply more stress. So they can have no strain energy. The original strain energy U will be released. This U energy then will be released. let us calculate amount of strain energy released associated with crack growth. Griffith obtained, obtained the strain energy as a function of crack length A. So we consider that the length of the crack is A. He obtained the following result for one half of the infinite plate as equation 4, which is U equal to sigma square over 2E into V, which is already demonstrated for this bar. This is the baseline value corresponding to 0 crack length when the material is perfect and is not broken. Minus sigma square over 2E multiplied by B pi A square. This term, that the term that subtracts from the strain energy, so it is subtracting from the strain energy, which is the baseline value. The term that subtracts from strain energy as the crack length increases according to A square. Equation 4 shows quadratic dependence on crack length. So it is quadratically dependent. So equation 4 shows quadratic dependence on crack length means that the change in strain energy with crack length at shorter length is very small, but then becomes very sensitive to crack length at longer lengths. So this is the physical meaning of this quadratic dependence. Griffith's failure criterion. So in this slide, equation 3, 4 has been shown, which are already derived in previous slides. The energy input required to break the atomic bonds and grow the crack is given by equation 3. So we have already shown this equation 3. As the crack grows, the stored mechanical strain energy decreases according to equation 4. So we have also given equation 4 in previous slide. So let us calculate total energy in the system by sum of these two equations 3 and 4. So we have equation 5. So this is the total energy of the system. So we can plot equation 3, equation 4 and equation 5. So what is the graph? The graph looks like this. On y-axis we have energy, whereas on x-axis we have length of the crack. So for atomic bond energy, which is given by equation 3, which is energy input required to break the atomic bonds and grow the crack as given by equation 3, it is a straight line. Whereas this red color curve, it is strain energy as a function of crack length as given by equation 4. And lastly, total energy is shown by purple curve, which is total energy in the system, and it is the sum of the two equations 3 and 4 and is given by equation 5. So this figure is about variation of total energy shown by purple color, atomic bond shown by this reddish straight line, and strain energy also shown by red curve with a crack length. So this is all about the variation. So what are the useful results from this graph? Let us study those results. For short crack lengths left of the maximum curve value, so if we divide this curve or total energy into half, so left of the portion, left of the maximum value of the curve, the total energy of the object increases with increasing crack length. So we are only discussing for short crack lengths, so the total energy keep on increasing up to the maximum value with the increase in crack length. But after that, the total energy drops sharply with the increase in crack length. So what does this mean? The total energy of the object increases with increasing crack length for short crack lengths. Therefore, additional energy must be input into the material in order to cause the crack to grow. So up to maximum value we need to supply energy in order to grow the crack. What happens next? At longer crack lengths, right of the maximum curve value. So after the maximum curve value, the right portion of the curve, so as the length of the crack increases, an increase in the crack length leads to a decrease in total energy. You can see the decrease in total energy. This means that crack can grow without any additional external input. So we can say that the once to initiate cracks we need to supply energy, but once an appropriate amount of crack is produced, it will no longer require energy. It will automatically uh, grow the crack and finally lead the breaking of the material. Finding the length at which the unstable crack grow. So let us find that value of length. Let us differentiate the total energy curve. So we have this total energy curve given by equation 5. So in order to find the length at which the unstable crack grow, let us differentiate the total energy curve with respect to crack length A. So we are differentiating equation 5 and then set the derivative to 0 in order to find the length at which unstable crack grow. Unstable crack means crack that can grow without any additional external input. So we are taking derivative of equation 5 and then putting it equal to 0. Cancelling B from the terms and solving for sigma stress, we have the following expression given by equation 6. And this 2 gamma S can be replaced with GC. The subscript F, sigma F, the subscript F has been added to sigma to signify failure of the material. Failure means when the material is broken. Equation 6 shows that, so we can conclude failure stress, so this is the failure stress, increases with the square root of the bond energy gamma S. Failure stress decreases with the square root of the crack length A. And Griffith critical energy release rate is given by Gc, which is equal to twice the bond energy gamma S. Here is the list of study material that consists of important books on material science and engineering, and one of the educational resource web link. Students can go through these materials in order to develop sound understanding on the aforementioned topics. Thank you for having me. That's all.